Welcome to part 1 of the course. Part 1 is an introduction to the smoke control system design in general. In part 1, I'm going to cover the following subjects. The first subject is the smoke control system design objectives as defined by the international codes and standards. The second subject, which is the smoke control system classification, so that you can have an idea on the classification of the smoke control systems in accordance to the right source, which is the related international codes and standards. And the third subject will be the factors that are affecting the smoke movement within an enclosure or within a space or within a building. And lastly, I'm going to give you an organized view on the related international codes and standards, and this will be very handy and very helpful during a submission and during the preparation of the design of the smoke control system for more reading purposes or for a reference in case it is required during a submission or during the preparation of the smoke control system design calculation report or a basis of design report. So without further ado, let's dive right into it. If we refer to chapter 4, which is titled as the design fundamentals in NFPA 92, which is the standard for smoke control systems, we can find a clear definition of the design objectives of the smoke control system. You can find in this paragraph that the methods for accomplishing smoke control shall include one or more of the following. The first design objective is to achieve the containment of the smoke to the zone of origin by establishment and maintenance of the pressure difference across the smoke zone boundaries. And the second objective, which is the management of smoke within a large volume space and any unseparated space that can communicate with the large volume space. So what does this mean? This means that the smoke control system have two main design objectives. The first objective is simply to contain the smoke and minimize it from spreading outside the boundaries of the area that have an active fire. And the second objective, which is to manage the spread of the smoke in a large volume space with a special attention to the open spaces to the large volume which are not separated from this large volume or unprotected or unfortified against the spread of smoke. And also, if we refer to paragraph 4.1.2, we can see that the specific objectives to be achieved over the design interval time shall include one or more of the following. The first objective, which is containing the smoke to the zone of fire origin. The second objective, which is to maintain a tenable environment within the exit stairwells for the time necessary to allow the occupants to exit the building. The third objective, which is maintaining a tenable environment within all exit access and smoke refugee area access path for the time necessary to allow the occupants to reach an exit or a smoke refugee area. And the fourth objective, which is to maintain the smoke layer interface at a predetermined elevation, especially in large volume spaces. So to simplify these objectives, the first objective is simply, as we said, just contain the smoke within the limits of the zone of the active fire. And the second objective, which is to maintain a tenable environment to allow the occupants to egress the space safely. And this is similar also to the fourth objective and the third objective, which is simply to control the smoke layer height to prevent it from filling the space, just to provide a necessary time for the occupants to evacuate the building safely. So if we're going to put the classifications of the smoke control system in a structured figure, as quoted from NFPA 92, we can see that the smoke control system have three main purposes. The first purpose, which is to achieve the smoke containment, and this is shown on the screen under the orange color. And the second purpose, which is the smoke purging. Smoke purging is usually required after the fire has been extinguished in order to clear the space from any residues of the combustion or the smoke accumulated within the space during the fire. And the third purpose of the smoke control system, which is to achieve the smoke management, and this is shown on the screen on the blue color. So basically, the smoke containment system, which is referred to by the orange color on the left side of the screen, this is achieved by creating a pressure difference, and the pressure difference is responsible usually to minimize any smoke spread outside the area having the active fire scenario. And this is done by one of the five methods. The first method, which is the stairwell pressurization, and this is simply to sustain a pressure difference inside the staircase and to maintain the staircase under positive pressure to minimize any smoke spread from any active fire zone into the staircase. And this is very important because all the occupants within the building will escape the building through the staircase, the exit staircase. That's why it's crucial to prevent any smoke infiltration inside the staircase. and the second method to achieve the smoke containment, which is the zoned smoke control. Zoned smoke control, simply defined as you maintain a sandwich of pressure difference, and this is usually done in the high-rise building. Let's say, for example, if a fire happened in the middle floor, this means that you will maintain a negative pressure in this active fire floor, while you will maintain a positive pressure in the floor above and the floor below. This is usually done in order to prevent any infiltration from the smoke within the space having the fire to the floors above or floors below. And the third method, which is the elevator pressurization. Elevator pressurization is done in order to maintain a smoke-free area within the elevator shaft. And this is very important also because if any smoke infiltrated into the shaft of the elevator, this means that anyone inside the elevator will suffocate from smoke. And this also means that the smoke can spread vertically freely from floor to floor if there is no any obstruction that prevent the smoke spread vertically within the elevator shaft. And the fourth method in the smoke containment, which is the refugee area pressurization. And this is a very common smoke containment technique that is usually utilized in the high-rise building to provide a smoke-free area or a pressurized area or a safety protection area for the occupants on the high floors. Let's say, for example, that the fire happened in the middle of a high-rise tower, so the occupants at the top floors will escape through the stair downward until they reach the exit from the building. But in some cases or in some scenarios, the smoke spread can cover the entire tower and prevent or make it difficult for the occupants to evacuate the top floors. So in this case, there are some refugees area that the occupants can stay inside until the firefighters reach the place or until there is a suitable opportunity for them to evacuate safely. And the last method of the smoke containment, which is the vestibule pressurization. Vestibule pressurization is the protection of the opened or the spaces open to the large volume enclosure such as an atrium. And this is very common in malls because in atriums you can find some spaces or some corridors open or shared between the atrium and the typical floors. So it is necessary to prevent any smoke infiltration from the atrium to these corridors of the typical floors, because if a fire happened in the atrium, this will mean that the smoke can spread vertically freely in these corridors and cause an untenable condition or unsafe conditions in these typical floors. That's why it's very important to prevent any smoke infiltration into these corridors, especially the corridors that are open to the large volume spaces such as the atrium. So in general, we can see that the smoke containment methods, the 5 methods, are usually utilizing one main item in order to prevent any smoke infiltration, which is the pressurization, or to create a pressure difference that will protect the occupants from any smoke infiltration, from zone to zone, or from fire or smoke zone to another occupied zone of the building. Second purpose of the smoke control system, or the second operation mode, which is the smoke purging mode, and this is usually done after the fire has been extinguished by applying a certain number of air changes to suck the smoke from the space and to clear any smoke residuals or combustion residuals from the building. And the last smoke control system purpose, or the operation mode, which is the smoke management. Smoke management does not aim to maintain the area free of smoke. This is very important to be clarified. But smoke management ensures that the conditions inside the space will be tenable until the occupants have enough time to escape, which means that the smoke management system extracts the smoke from the space or contain the smoke within certain enclosures in order to give the occupants enough time to egress or escape from the space having the fire safely. And this is usually done by one of the following 4 methods. The first method, which is the mechanical smoke extract. Mechanical smoke extract is done in order to either control the smoke layer height or to slow down the smoke descent. This means that you employ smoke extract fans at the highest levels, and these smoke extract fans suck the smoke from the zone having the fire in order to control the smoke layer height and prevent it from descending lower, or in order to slow down the rate of descent until the occupants have enough time to escape. And the second smoke management technique, which is the smoke filling reservoir, and this is seen clearly in the large volume enclosures or in the industrial applications In these scenarios, you can find a or a relatively large enclosure above the ceiling, and this relatively large enclosure, like a dome, maybe this dome is circular, maybe this dome is rectangular, and it is intended to store or to be as a smoke reservoir to contain the smoke for a certain amount of time, to prevent it from descending or to slow down the rate of descent of the smoke, which will give the occupants enough time to escape. And the third application of the smoke management system, which is the natural smoke heat vent. And this is also done for two purposes, or for one of two purposes: either to control the smoke layer height or to slow down the smoke descent. Control the smoke layer height, which means that the system will maintain a smoke layer height at a predetermined level, and this is done via the application of the specified calculation related to this. Or the second purpose, which is to allow the smoke descent but in a slower rate, and this rate or the slower rate will allow the occupants to evacuate the space safely and will give them enough time to escape the place without being suffocated by the smoke. The fourth application of the smoke management, which is the airflow method, and this is done by the application of supplying an airflow to the communicating spaces or the spaces joining more than one spaces, especially in the large volume enclosures such as the atriums. This is done by supplying air to the corridors to prevent the smoke from traveling from the atrium to these areas, or to minimize the smoke spread into these areas. So now we are going to discuss the smoke control system classification in accordance with ASHRAE. ASHRAE classifies the smoke control systems into 5 methods. The first method, which is the compartmentation, and the second method, which is the pressurization, and the third method, which is the dilution, the fourth method, which is the airflow, the fifth method, which is the buoyancy. The first method, which is the compartmentation, this is done simply by the application or the addition of barriers to limit the horizontal spread of the smoke and the horizontal exposure to the smoke, which means that if I have an open floor area, this open floor area, if any fire happened, the ceiling jet or the smoke jet on the ceiling will spread horizontally in everywhere. But if I put barriers, these barriers will minimize the spread of the smoke and will divide this open floor into sub zones or subdivisions. Each division will have a smoke enclosure or a smoke reservoir. This smoke reservoir is limited by the depth of the smoke compartment. And the second method of the smoke control system, which is the pressurization. Pressurization, as we have explained earlier, is the application of a pressure difference within the space that you need to protect. And this is done simply by pumping air to prevent the smoke infiltration inside the space you want to protect. And the third method of the smoke control systems, which is the dilution. Dilution is the basic concept of the smoke control system, and it is done usually by extracting air from the space and supplying air into the space, but the supply air and the extract air ratios are different, which means that if you want to maintain the space under negative pressure, then the extract will be more than the supply. But if you want to maintain the space under positive pressure, then the supply will be more than the extract. And this in turn dilute the concentration of the pollutants and the smoke from the space. But it does not contain the smoke in the space. It dilutes the harmful effect of any pollutants or smoke within the space. And lastly, the last concept of the smoke control systems in accordance with the ASHRAE, which is the buoyancy. And buoyancy is the thermal property of gases. It's simply defined as the hot gases rise up and the cold gases fall down below. So we can utilize this by extracting smoke from high points, because smoke is a hot gas or a mix of combination of hot gases. So by default it will rise up. And this means that you can store the smoke at the high level in a smoke reservoir, or you can extract it from the highest point. In this video, I'm going to discuss the factors that affect the smoke movement within a building. I'm going to start by discussing the stack effect. Stack effect is a phenomenon that happens inside the buildings, and it can be seen especially clear inside tall buildings. Stack effect is a phenomenon driven by the temperature difference outside and inside the building. This means that the climate inside and outside the building will determine how the smoke will spread, especially in high-rise and mid-rise buildings. If it's hot and humid outside, but it is cooled and air-conditioned inside, smoke will initially flow up, but then it will start migrating downward. This is due to the fact that the cold air inside the building have a relatively higher or bigger density than the hot air outside the building. So the air in the top floors will start to flow down, and it will exit from the low areas inside the building, and this will be compensated by a cold air from the upper floors again. So the movement pattern of the air in the large vertical enclosures like the shafts and the stairs will be from top to bottom. This will mean that if a fire happened in the upper half of the building, it will start to spread vertically downward in the shafts, although there are no need or there is no motive to make it spread vertically downwards. And this is very dangerous for the firefighters and the occupants when they try to egress the building. And this is known as the reverse stack effect. And this is a phenomena that happens usually in the summer, while the opposite is true. In the winter, when the ambient air inside the building is hot, relatively hot or warm, and the air outside the building is cold, this means that the ambient air inside the building, due to its lower density, because it's higher temperature than the outside, it will try to flow upward. And this can be seen clearly in the open shaft, the shafts that are open vertically like the staircase enclosure and the elevator enclosures. This means that if a fire happened at the lower floors, the fire, once it reaches the staircase, it will be driven upward relatively fast due to the stack effect. This also means that in these conditions in the winter, the smoke will migrate to upper floors that are remote from the fire, and this is known as the stack effect, and it's usually a common phenomena that happens in the winter. You need also to know that if we are going to look to the building from a stack effect point of view, there is a plane that is relatively near the middle of the plane, which is known as the neutral plane. This neutral plane does not have any forces affecting on the stack effect, and if there is any smoke present in this area, it will not be driven to flow upward or downward. This neutral plane in the symmetrical places or in the simple geometry places or buildings can be near to the middle. However, if there are openings or unsymmetrical shapes of the buildings, it will vary and it doesn't necessarily have to be on the middle of the building. And at the standard atmospheric pressure, the pressure difference caused by either of the normal or the reverse stack effect can be expressed through the equation which is shown on the right side of the screen. This equation equals delta B for the stack effect equals 7.63 multiplied by the reverse of the temperature difference between the indoor temperature and the outdoor temperature multiplied by the Z. And the Z is the distance from the neutral plane. So if you also refer to the table below, which is table 1, you can see that this table summarizes the effect of the stack effect in a numerical way. You can see this table consisting of 4 columns. The first column, which is the building height, and the second column, which is the outside temperature, and the third column, which is the inside temperature, and the fourth column, which is the delta B or the pressure difference exerted on the building due to the stack effect. You can see that in the first row, if the building height is 75 feet or approximately 25 meters, let's say 8 floors for example, you will have a stack effect, a pressure difference of 0.08 if the inside temperature is 70 Fahrenheit and the outside is 0. Outside is 0, which means that the outside is very cold during the winter. So you will have a positive stack effect on the lower parts of the building equal to this value. However, if the building height increased to 2,133 feet, you can see that the stack effect will be 0.72 inch water gauge. And this is very huge pressure difference exerted on the gaps and on the walls of the building. This can cause a failure of the pressurization system for the vertical enclosures like the staircase and the elevator. This is why it is important to study the effect of the stack effect and the reverse stack effect, especially in high-rise building, while considering the design for the pressurization systems. Also, for further explanation, you can refer to the figure 5, which is shown on the bottom right side of the screen, and it shows you the pressure difference between the building shaft or the building staircase and the outdoors, which is caused by the normal stack effect. If we refer to the figure on the left side of the screen, which is the normal stack effect, you can see the flow pattern is upwards. This means that the air will enter from the low level and it will reach the top level and go out from the top level. This means that on the low level of the building you will have a negative pressure due to the suction of the air, while on the upper floors or the upper levels you will have a positive pressure. And this negative and positive pressure with respect or with relation to the neutral plane can be represented on this figure 5 shown on the bottom right side of the screen. While in the reverse stack effect, this figure will be flipped, which means that on the bottom side of the building there will be a positive pressure, while on the top side of the building you will have a negative pressure exerted on the shaft enclosure. Wind also can have a profound effect on the flow of the smoke or the spread of the smoke inside the building, and this is especially clear in the high-rise buildings. This is because when the wind flows over a building, or when the wind exerts a flow on a building, it usually hit the building from one side. And when the wind hit the building, or when the wind direction hit the building, let's say for example on this figure on the left side of the screen, if there is a wind condition and it is exerted on a building, it will hit it from the left side, and then it will flow over it and go to the right side and continue the flow of the wind. So when the wind hit the building from the left side, it will exert a pressure on the building. However, this wind, because it's facing an obstruction, it will form vortices and turbulence. These vortices and turbulence will create a pressure drop, and this is especially clear on the other side of the building, which is the side that is not facing the wind. This side, usually when the flow of the wind fly over the building and around the building, it forms vortices downwards or after the building, and these vortices and the turbulence create a negative pressure or a suction pressure, or create a partial vacuum, or to simplify it, it creates a pressure drop. This means that if there is a fire situation happening on the direction where the wind is hitting the building, the fire will face a positive pressure from outside the building. It will infiltrate to the building in the form of a positive pressure. However, if the fire is occurring on the side which is not facing the wind, there will be a negative pressure outside the building, which means that the smoke will be driven to flow from the building outside due to the negative pressure outside the building more than the pressure inside the building. And this is also can be seen on the ground level or on the low levels, because due to the turbulence and the vortices forming wherever it's formed, this means that this is a low pressure region, and this region will be subjected to exfiltration from the building outside. This means that if a fire happened inside the building, the flow of the fire or the flow of the smoke can be driven to flow outward or inward depending on the pressure exerted by the wind, and this pressure difference can be expressed in this equation on the right side of the screen, which is a function of the velocity and the density of the air, and the pressure coefficient, which is related to the design of the building. We can see that this equation refers to the pressure of the wind or the wind pressure as PW, and PW equals 0.00645 multiplied by CW multiplied by the rho multiplied by the square of the velocity. U is the velocity at the wall height of H, which is the wall height of the building, and rho, which is the outdoor air density, and C, which is the pressure coefficient, which is related to the figure or the design of the building. So the pressure coefficient CW depends on the wind direction and the building geometry as well, and the local obstructions outside the building to the wind. The pressure coefficient are in the range usually of minus 0.8 up to positive 0.8, and the positive value are usually expressed in the windward walls, which are the walls that are facing the flow of the wind, while the negative values are for the leeward walls, or the walls that are on the back side or on the downward side from the wind flow, which are not facing the wind flow, or the sides that are having the turbulence and the vortices formation. That is why it is very important to calculate the wind pressure, especially in the design of the pressurization system for the vertical shafts or the vertical enclosures like the staircase. Because if the wind pressure is exerting more pressure than the pressurization value inside the place, this means that you will not have the desired pressurization inside the space. For example, if I have a wind pressure of 0.5 inch water gauge, while I am maintaining 0.1 inside the staircase, this means that the staircase is no longer positive, because there is a pressurization exerted into the staircase from the outside air. That's why it's important to study the variation of the relationship between the pressure difference outside the building, like the pressure difference related to the stack effect and the wind pressure, with respect to the pressurization of the vertical shafts inside the building. Now, the third phenomena or the third factor that is affecting the smoke movement from and to the space, which is the buoyancy effect. And buoyancy effect can be simply expressed as an upward force. This upward force is driven by the temperature difference between two gases. One of them is cold and one of them is hot. The hot gas will be driven upward or will flow upward because it have a lower density or a smaller density, while the cold gas have higher density, so it will be heavy or relatively heavy, and it will stay at the lower portions of the building. So when we apply this to the figure on the right side of the screen, which is a representation of a simple house, in the case of a fire, the smoke, due to its hot temperature, it will flow upward, and it will flow to all the partitions up inside the high level of the building. Also, it will flow through all the cracks and all the openings that are located at the high level. This can be seriously dangerous in the high-rise buildings or in the buildings that have more than one vertical floor or one vertical enclosure, because due to the buoyancy effect, the smoke will spread quickly at the high level. And this can be also dangerous in cases of the large open volume spaces like the atrium, because this means that the smoke will not only fill the atrium, it will fill the high level of the atrium, and from it, it will spread into the common corridors or the communicating spaces, and in turn, it will penetrate or infiltrate the floors located at the high levels. This means that even if a fire is happening at an atrium ground floor, it will fill the top floor with smoke before even the ground floor fills with the smoke, and this is due to the buoyancy effect of the smoke. And this in turn exerts a pressure difference due to this upward force, and the pressure difference can be expressed from the equation on the left side of the screen, which is a delta BFS. Delta BFS is the pressure difference from the fire compartment to the surrounding, expressed in inch water gauge, and it equals 7.63 multiplied by Z, which is the distance above the neutral plane of the room or of the building, in case if it's a high-rise building. And this is multiplied in the inverse of the temperature of the surrounding and the temperature of the fire component. This means that the smoke will exert a force on all the vertical openings and in all the openings in the space due to the buoyancy effect resulting from the temperature difference or the variation in the temperature difference, which means that if a fire happened inside a room, it will exert a pressure on all the surrounding rooms that can be expressed from this equation. That's why it's important to study the effects of the buoyancy effect in case you are applying a pressurization into a specific volume or a specific enclosure that is expected to have a fire scenario. Because if the buoyancy effect pressure difference is exerting a positive pressure in the space, which have a higher pressure difference value than the value you are using in the pressurization system, it will almost cancel out the pressurization system. That's why it's very important just to cross-check the pressure difference that is resulting from the buoyancy effect in case of a fire. The last factor that affects the smoke movement and smoke spread inside a space is the expansion effect of the hot gases and the smoke. As we all know from the ideal gas equations, when the temperature increase of a certain gas, the volume also increase. And if the volume did not increase, the pressure will increase. This means that in case of a fire that happened inside an enclosure, the fire usually produces smoke in the form of soot and other combustion products. This smoke will be relatively hotter than the ambient air within the space enclosure, and this temperature difference will mean that there is a volume difference, which means that, let's say for example, that if the temperature of the smoke generated by the fire is double the temperature of the building itself, or the ambient air inside the building itself, this will mean that the volume of the smoke will be also double the volume of the ambient air, which also means that in case of a big fire, the smoke temperature will be more than double the ambient air. It can sometimes reach 120 degrees Celsius or more. And this means that the temperature of the smoke or the hot gases will be more than double or more than triple or quadruple the temperature of the ambient air. This will mean that the volume of the smoke will be intensified, and it will take a lot of volume of the internal space. And the increase or the sudden increase in the volume will exert a pressure on the space. And this is very dangerous because it can increase the pressure significantly inside the space if the space is airtight or sealed. And this we can see on the videos that are available online. In some scenarios, when the firefighters open a space, it explodes, and this is due to the fact that the pressure inside has increased significantly due to the expansion effect of the smoke inside the space, while there is no ventilation or venting for the excess of the volume of the smoke or for the excess pressure exerted by the smoke to the closed enclosure of the building. And this is a very dangerous phenomena that needs to be studied and evaluated, and that's why providing the system or the place with a ventilation system that can be active during the fire, which is known as the smoke control system or the smoke management system, is very, very important, because it minimizes the harmful effects such as the sudden increase in pressure related to the sudden increase of the volume of the smoke inside the enclosure, by providing the ventilation to provide means to control the pressure inside the place and to minimize any sudden pressure increase, and also to dilute the harmful effect of the smoke.